Thanks, Emmanuel. And hello to everyone. I see there is a big group here, so well done on coming together with all these people. Seems like a very active meetup. Congrats on that. I know that maintaining a big community is not easy. So thanks a lot for doing that, and thanks for your kind introduction and great feedback with the podcast. That's always interesting to hear. So as you said, I have some stuff for you today about Bayesian stats, and I think the best is that I share my screen with you, which is, I think, the case, right? Do you all see my screen?
Yeah, good for us.
Perfect. Awesome. Very happy to be with you today. As you can see, I have my podcast mic up to talk to you to make sure the sound is good. And so that's why you see this big, weird black ball on the camera. Usually you don't see it in podcasts because, well, that's only sound. But today, I have to make with that. Hope it's not too much of a diversion for you. As Emmanuel said, today I'm going to talk about Bayesian modeling, mainly without the math. There can be a lot of math in Bayesian stats, but today I'm not going to focus on that. Again, my name is Alexandre Andorra, but if you're not a French speaker, you can go with Alex. I know that's hard to pronounce for non-French speakers, so I'm totally fine with Alex. And I work at a Bayesian consultancy called PointC Labs, where I am a principal data scientist and co-founded that with a bunch of very brilliant people that I'm going to talk about next. But first, as I am very selfish, I'm going to talk about me. Actually, I didn't even do economics. I come from even further down the non-math path because I did business school first. So first studied management and then did a double degree in political science. And that's where I went a bit more into statistics and discovered about Bayesian stats. Happy to talk about that in Q&As if you want, but that's not the main point for today. As said, I am a PointC and RVs author, or co-developer, as we say in the open source world. And I am the host and creator of the Learning Bayesian Statistics podcast. As far as I know, the only podcast dedicated to Bayesian stats out there. Feel free to listen and give me some feedback and guest suggestions and so on. It's always great to hear from listeners. And lastly, my specialties when started Bayesian stats were studying elections and more broadly human behavior. Although now I just love building models, whatever the field. But I started mainly doing these kind of models from the social sciences and electoral forecasting, etc., which is still dear to my heart today, although it's not my main field anymore. So as I was saying, I am working at PointC Labs with a bunch of people who are the inventors of PointC 3.2, and combined, we do have decades of experience building Bayesian models. And what I really love about the team we have is it's super diverse. I see that every day and I experience it every day. It's just a joy to work with people who come from academia or mathematicians or neuroscientists, or we even had a former SpaceX rocket scientist. So it's just, it's great to work with so many people with so many diverse backgrounds. And the funny thing is that you have such diversity also in the applications in industry where you can find PointC 3 used. I mean, you have problems in many domains that meet the criteria needed for Bayesian stats, as demonstrated by our customers that we have in diverse fields that range from finance, biotech, agriculture, pharma, ad tech, supply chain. I mean, you can see there is a huge diversity here. And also, if you're more into research in academia, PointC is also quite used in academia. As you can see here on this slide, not going to spend too much time on that, but yeah, if that's your stuff, I know that you can use PointC in your papers, and actually the person who created that originally created that during his PhD thesis to help him model some ecological statistical model. And you might have a question, wait, is PointC the only library that allows me to do Bayesian stats? The answer is no. There are a lot of Bayesian stats library out there. We are, though, the main platform in the Python ecosystem, I'd say. And the difference I think we have is that we've specifically designed PointC to be easy to use for practitioners. Another leading software in many respects is Stan, the Stan library, which is really great, but is more targeted to researchers and has its own, let's say, compiler, and it's kind of its own ecosystem and language, but really great quality too. And now I'm going to dezoom even more than what I did here, and just go into why would you use Bayes at all in the first place. And by the way, while I'm running through those slides, really feel free to interrupt me and ask questions along the way. That's always useful. Sometimes I can jump too quick on some explanations or conceptual, so yeah, feel free to jump in. Otherwise, I think we have a Q&A at the end of the other presentation. So either way, happy to answer your questions. So yeah, when would you use Bayes? What are the best cases? From what I see from my own experience, but also from our customers at PointC Labs and from the people using the open source package PointC3, often those are people who need to understand their business. So not only having a model that does something and spits out something, but you don't understand it and you can't really interpret it. Often we have people who want an interpretable model, and that's really one of the main use cases. Another one, very important too, is to integrate domain knowledge in your models. So either that can be really be in any domain. All of the domain I showed you in previous slides, they often have knowledge that they need to use, and so here Bayesian stats really shine. And that's actually related to another case where they are particularly useful. It's when you have sparse or noisy or missing data. So when your data are not really trustworthy, and so you need something else, you need prior knowledge, prior scientific knowledge to complete the data and be sure that your inferences are more robust and get less trapped, let's say, by idiosyncrasies in your data. And still related to data, a case we often see is people with structured data. So that could be hierarchies. For instance, let's say you have a marketing data set and it comes from several countries. In each country, you have several regions. In each region, you have several cities. That's perfect for the Bayesian stats framework. You can easily add these hierarchies into your model, the structure of the data generating process. And of course, I think you know that another kind of structured data, which causes a lot of headaches, usually are time series, but you have other stuff as well. Another case where we see Bayesian stats very useful is when you're not having a simple prediction problem. This is related to the first case I was telling you about. So you need an interpretable model, but also you don't just need you don't just have tabular data that you put into a black box and makes a prediction. You need a model that can be interpretable, but also sometimes do causal inference. And then again, Bayesian stats can be very helpful. Related to that, often with causal inference or predictions, you need to make decisions with real world consequences. So for instance, in supply chain, you have a model that tells you when this part or these other parts is gonna arrive, and then you need to make decision based on the outcome from that, and you need to minimize some loss or maximize some profit. Well, then you can do what's called Bayesian decision making, and that allows you to take into account the full distribution of uncertainty in your model and data, and then make decisions accordingly and optimize those decisions and the gains and losses you witness from them. And the last case we see at PointC Labs, or in general, is just interest in Bayesian stats, but people who don't know where to start. And so I get that a lot with people listening to the podcast, for instance, or with some customers like that who need, for instance, some corporate workshop where we come and teach them, okay, what's Bayesian stats, what is PointC3, how can you do that, etc. So I think the logical first place from there is just to tell you what Bayesian stats is, actually. And that's what I'm going to do now. Any questions first before I dive in? Okay, perfect. So yeah, let me have a comparison that we like to make at PointC Labs because we are a bit witty. And it's to compare black box machine learning and Bayesian modeling as pre-made easy cooking on one side and handmade cooking on the other side. And so on the first side, you have something that's pre-made, so it's easy to cook. And you have a one size fits many thing, and you don't have to learn more about the ingredients. You just put that, and that's usually good, but you can't customize it. And often it's more expensive, or it requires more data if you want. Whereas in the other case, in the handmade case, you can do a lot of stuff. Yes, it requires skill, and you need some recipes to guide you. But the great thing is that you can include dietary constraints. So here, that would be expert knowledge in our comparison. You can also tailor your food exactly to your taste, exactly what you need. And also, let's face it, that's just healthier to cook your own food, right? So let's just keep that in mind. Now, let me take an example. Let's take a very concrete example that I'm sure many of you are quite comfortable with and know about it. And it's A/B testing. So very simple. We have one version of the website where we have, let's say, a red sign up button, another version of the website where we have a green sign up button, and we want to know which version of the website works best. So we have a control and we have a variation, but we could have several variations. But for the sake of simplicity, let's just use one variation here. And let's say that our marketing department comes back to us with some data. Here, they are quite simple. They are just the observed conversions for version A and for version B. A 0 is not converting and a 1 is converting. So what can we do with that? Like, you can ask yourself the question right now, and maybe one of the answers you had is, well, let's just take the mean. In one case, we have 7% conversion. In another case, we have 17% conversion. So yeah, there you go. B is better. Yeah. You can do that if you want. Something is missing here, though. Do you see what's missing here? Okay, I'll let you know. It's uncertainty. Like, how sure are you that B is better than A? Because you have a finite sample of people who have clicked on A and B, or who have even visited A and B. This sample can also be biased. This sample can also be unbalanced. Many more people saw version A than version B. So, okay, maybe if you have a biased sample, then maybe just people who are more likely to click on B who saw B, and then you improved your conversion rate for B, but it's not actually representative of what it would do if you deployed that into production. So yeah, something is missing here, and what's missing is having a model of the data generating process. And so let's do that. Let's assume that we have a magic machine which provides plausible values of conversion rates, okay? Because actually there are multiple plausible conversion rates that could explain the data we have, the data we saw. So we start with our data, we have zeros and ones, blah, blah, blah. We put that in our magic machine, and then boom, it spits out plausible values of conversion rates for A. So as you can see, there are multiple plausible conversion rates. It could be 11%, 8%, 5%, 9%. So it's not only 7% that's plausible with the values we observed. So what we can do here is just plot a histogram of those values. And if you do that, on the right-hand side of the slide, you see this histogram, which goes from pretty low values, actually. 2.5% is not very probable, but it could happen in some versions of the reality that the conversion rate for A is that low. But it could also be much higher, around, let's say, 13%, for instance, is not a zero. That's interesting, right? Because now we have a more fine-grained understanding of our data, and most importantly of the process that generated the data. That's what we want to understand, right? And we can already do interesting things actually with what we got here, because we get some plausible conversion rates for A, some plausible conversion rates for B, and maybe we're asking, okay, how many plausible values are above 10% for website A? Okay, well, then I just have to count how many plausible values are above 10%. Well, it's about 18% of them. So you have it. The answer is 18%. So what we're doing here is already statistics. Like we can go back to the marketing department and tell them, okay, according to our data and our model, the probability that the conversion rate for A is above 10% is 18%. This probability is 18%. So that's already quite good and actionable, but often what we're interested in an A/B test is this. Okay, but I need to compare A and B actually. That's the crux of the A/B test. So how do I do that? I have conversion rates for A, conversion rates for B. How do I do that? Well, very simple. In the Bayesian stats framework, you just look at the difference and you look at where plausible conversion rates for A are larger than that of B, and you just count how many samples are in these subsample compared to the whole sample you got before, the whole sample of plausible values. And here, it's the same story. We can go back to the marketing department and tell them, okay, the probability that the conversion rate of A is larger than that of B is 1.8%, like around 2%, let's say. And then, well, I let you decide with your marketing department what conclusion you can draw from that and which action you can take from it. But at least it's quite actionable, and you squeezed more information from the data because you were able to estimate the uncertainty in your estimates. Now, maybe you may have questions about this machine, right? Like, Alex, how do we build that? Because I don't have this machine. So if I want to do that, that sounds interesting, but I need to build this machine. Well, rest assured, that's where our dear Thomas Bayes is coming in. And what's that about, right? So let me show you how you can think about what we just did. So we have our data on the left bottom corner, and then we have a solution generator, which is the values for the latent parameters we are trying to estimate. So here, the conversion rates. And they are pretty different, as we saw. So we can have a lot of different values for that explain the data. And then we have our solution evaluator. And for each of the plausible solution that the solution generator provides the solution evaluator, it will classify, if you want, each of the plausible solution. The implausible one, it will discard. The plausible one, it will store them. And that's the plausible conversion rates for A we got before, right? You remember the histogram plot, the blue histogram plot that you see here, again, on the right top corner of the slide. This is just how it works. Of course, though, as you know, this is statistics, so we love to have not very understandable lingo so that you are all lost when you start learning Bayesian stats. So how do we call that? How do Bayesians call all of these? Well, our data is still our data, but our solution generator, that's called an MCMC sampler. MCMC, what the hell is that? It's a Markov chain Monte Carlo sampler, but yeah, you don't know, at least to start, you don't know to really understand what this stands for. Just think about it as a solution generator. Then our solution evaluator in the middle is our Bayesian model, because our model is basically our story about how the data could have been generated in the world as we conceive it. And so that's, yeah, our model. Then the implausible solutions, well, we discard them, so we don't give them any name. But the plausible solutions that were stored, that's what we call the posterior samples. And that's one of the most important concepts in Bayesian stats. That's what you use to ask a number of questions afterwards to do your analysis, as we already did before with the questions about the conversion rates. Okay? So now your question could be, but how do we evaluate the solution? That's a very good question. Because yeah, it's very important to have a proven way to evaluate this solution. And so the question is here, out of 100 visits, we got 7 conversions for version A. So which conversion probability plausibly explains the data? And this evaluation function is what we call a likelihood. And here, in our case, as inputs, it takes the number of trials, which is 100, and the number of successes, which is 7. And finally, the conversion probability we want to estimate, we want to infer. And then it returns how well this conversion probability explains the data. And this likelihood function that we just described in statistics, it's called a binomial distribution. And I'm sure you already saw what that means somewhere, sometime, maybe in your high school statistics classes. But the binomial distribution is one of the most well-known. in statistics, and that's what we're using here to evaluate the plausibility of our data, which is the likelihood. And then we need, a key part is that we need to update the space of plausible solution. So if you remember, we had our prior space of plausible solutions. So these are our plausible conversion rates for A before we see any conversion data. So let's think about it. It has to be, what are the constraints on such a rate? Well, it's a rate, so it has to be between 0 and 1. Okay. Can it be exactly 0? Yeah, quite rare. Can it be 1? No, impossible. Like, no website in the world has a conversion rate of 100%. Maybe in North Korea, I don't know, but not here. So yeah, very skeptical of such values, even before seeing any data. Even a conversion rate of 80% is huge. So what we're gonna do is we're gonna use something called the beta distribution, which is a great distribution because it's very flexible, and at the same time it constrains all of its values to be between 0 and 1. So that's a great way to initialize your space of plausible solutions. And we're gonna find a beta distribution that has most of its probability mass. Here we put it between, well, 0 and 50%, let's say. It even goes to 60%. And so this beta distribution has most of its probability mass between these values, and even, let's say, 80% of its probability mass between 0 and 40%, something like that. Okay, it seems like a good way to initialize our prior space of plausible solution. Keep in mind, this is just an assumption, and you can go back to that and change it to see how your results are sensitive to this choice of assumptions, or if they don't change at all, or yeah, you can, this is an assumption basically, so test it and you'll see how it goes. So then we observe our data, we evaluate the solutions with our MCMC sampler and our Bayesian model, and we update our prior space to get, boom, our posterior space of plausible solutions. And here, with the data we got, well, the model is telling us, actually, the plausible solutions after seeing the data suggest that your conversion rate is, well, much more on the left hand of the distribution, on the left tail of the distribution, right? It's most probably between 5 and 15%, with most of the probability mass after seeing the data being around 10 and 50%, which makes sense, right? And it's like, this is what we were expecting, both from prior knowledge and from the data we observed. But that's reassuring that we got that right. So now we have everything, right? We can write our model. But how do we do that? Again, good question. How do we do that? Well, we fire up PyMC3. We import it, usually as PM. We open a model context, give our model a name, and then we go into it. We define our prior solution space. This is the conversion rate we want to estimate, remember? So that's our beta distribution, our plausible solutions before seeing the data. And after some trial and error, and also after having some intuition, after a while doing Bayesian stats, you know that the beta distribution with alpha 2 and beta 10 gives you this shape here that you see on the right. So you use that as the prior. And then we define our likelihood. Remember, that was a binomial distribution. And this distribution has here 3 parameters. The first one is the number of trial, simple, 100. Another one is P. So that's the probability, what's called the binomial probability. So that's the probability of a success. What is it here? Well, that's exactly our conversion rate. It's exactly what we were after. So that's great. We just put P equals conversion rate, and that tells PointC, okay, here is how these two variables are related. And the final keyword is just the observed keyword, and that's the number of successes we observed. And having this keyword here, observed, tells PointC that this is our likelihood, that this is not unknown, this is not something we're trying to infer, this is something we observed, and all that's up from there, these are priors, okay? And then we evaluate our posterior solution space, and in PointC you can do that very easily. You just call pm.sample, and it will automatically do that for you and give you back plausible values for the conversion rate of A. Pretty neat, right? And here I just added in a slide, at the top of the slide, if you want the statistical specification of the model so that you can see the correspondence between how you would write this model statistically and how you would write it in PointC3. And as you can see, the translation is pretty straightforward, right? Conversion rate follows beta 210, and how likely follows binomial 1 conversion rate. Okay, yeah, pretty easy, right? And that's actually something we're very careful about when designing PointC. It's to try and have model specification in code that are very close to model specification in math, in the statistical definition of the model. And now we can do statistics. We can compute what we computed before, what I showed you. You remember the probability that the conversion rate of B is below 10%. The conversion rate of A is below 10%. So that's what we do here. The great thing is that we get samples from our MCMC sampler. We get posterior samples. And so then it's pretty easy. Any question you have about your posterior samples, it's just counting. So here, let's just count the plausible values of A and the plausible conversion rates of A. How many of them are below 10%? Well, you get an array of true and false, and then you just compute the mean of that. And what does it give you? 0.82. So you've got an 82% probability that the conversion rate of A is below 10%, given the model and data you have. And if you remember, that's exactly what I showed you before. I told you that there is an 18% probability that the conversion rate of A is above 10%. So yeah, that fits with what I showed you before. And same thing, we want to know the probability that the conversion rate of A is better than that of B. Super easy. Just take the posterior values for A and posterior values for B. How many of them are above B? Compute the mean of that, and boom, 1.3% chance that it is the case. Again, it fits with what we saw. So as I told you, this is just counting, which is great when you get posterior samples. You just have to count the scenarios that you are interested in and compare that with all the other possible scenarios, and then you get your probability. And so that's pretty much my introduction to Bayesian stats for you. I have just one more slide for you before we go, I think, into some questions. And that's, okay, this is all very beautiful, but it's not magic, right? It's even better than magic, because here, you know the trick. In magic, you don't know the trick. Here, you know what's going on under the hood. And that's the great thing of modern MCMC samplers. The latest algorithms, they cry out loud when they fail. You know that pretty quickly if your model has a very big problem that could bias your inferences. And that's really great. Beginners usually hate that because that's very stressful. But actually, with time, you embrace that and you are thankful and grateful for all the tools that the latest algorithm have for diagnosing your inferences. And so these are effective sample sizes, the standard errors, the similarities between the chains. I'm not gonna dive into that right now, but basically when you run a Bayesian model, usually you run several what we call chains in parallel on your computer. Usually it's 4, and so you get 4 chains. That way the MCMC chains is initialized at a different point of the posterior space and allows you to explore the space more efficiently. And then a good way to diagnose your model is to look at the differences between the chains. And that's usually a way to spot if there are some problems. And finally, you have HMC specific diagnostics. So HMC, what does it stand for? It's Hamiltonian Monte Carlo. That's basically the state-of-the-art way of doing MCMC right now. That's what we use in PointC3. That's what they use in STAN 2. And these latest algorithms have even more tools for diagnosing your inferences. And those have sometimes weird names, but basically just have to learn them and understand what they mean. And then it's tremendous help to debug and understand your model. So these are the divergences, the tree depths, the step size. This is really great to better understand your model. So that's pretty much it. I still have a lot of slides to show you, especially, for instance, about the industry applications that we have of Bayesian stats that we see in PointC labs. And that's great to understand how you can use that. But instead of going through them linearly like that, I'd like to have a more interactive session, and we can have the Q&A session, and maybe some questions will be related to that, so I can show you some of those industrial applications or any other stuff that you can do with PointC3. So Emmanuel, I don't know if you want to take the floor back.